It's a great pleasure to join you. And I just wanted to start by thanking the organisers for making such an inclusive hybrid conference. I know how much work goes into making such a complex conference work and make it look effortless. And so I'm very grateful that everything's been very smooth from the back end, and hopefully it will be from the front end as well from your perspective. It's a real pleasure to join you because I think particularly for two reasons. First of all, really to celebrate and remember Dara O'Donoghue, because I think in my career, having those technical and really technically talented people who understand and can develop instruments and understand telescopes and systems in a deep way has really been the backbone of my team's success. I've been fortunate to build teams with those sorts of technical experts working very closely with observers and theorists. And I think those sorts of diverse teams produce really exciting and interesting science and help us to push new frontiers. But it's often that our technical colleagues sometimes get missed out in getting credit. So it's wonderful that this conference is to celebrate Dara. The second reason I'm really excited to be part of this conference is because throughout my career, I've been interested in black hole driven processes, in particular accretion, and more recently, probably in the last decade and a half, the most powerful and energetic sources in the universe, gamma ray bursts. And the big question my team have been trying to understand is what is the role and properties of magnetic fields, which were theoretically predicted to be important. I'm an observational astrophysicist by background, and I work across the electromagnetic spectrum. And of course, the way to really measure magnetic fields, and I don't need to tell everybody in the audience this, is to use polarisation as a unique probe. And really, for many of us who work in these fields, we are seen as slightly oddballs. Polarization has been a very niche technique. It's been traditionally very challenging. It's now, I think, coming into a new era of popularity. And I think this conference really epitomizes that. I know when David gave his introductory talk on the first day, that really chimed with me, because although we're all working in very different specialisms, we're coming together across our subject boundaries to answer some of these big questions. So I'm looking forward to connecting with you through this conference, and also afterwards, I hope, and continuing to learn from people in different subfields. So today I'm going to give a very whirlwind tour through gamma ray bursts. This will be a review talk. I will also sort of focus on my team's work as this has gone through. I've had many wonderful postdocs and PhD students go through my international team. And I hope that this talk will be broad enough so that those of you who know nothing about gamma ray bursts will get something out of it. Those who are experts in gamma ray bursts will also get something out of it and not feel too patronized by the broader overview. And I know that there are many other good talks through this session, and also the second gamma ray burst session, you'll hear even more really up-to-date results. And I'll allude to some of these as I go through. And then at the end, I'll be handing over to colleagues in this session and also in the second session. So gamma ray bursts are thought to be instantaneous luminous objects, the most instantaneous luminous objects in the gamma ray sky. And the little movie you saw flash up in the corner there shows when a gamma ray burst goes off, it actually swamps instantaneously the entire gamma ray detector for a few seconds. We think that they're producing the core collapse of massive stars, 200 to 300 times the mass of our own sun, or the merger of compact objects. And again, I'll talk a little bit about how we think that picture is becoming more complex. The reason that they're interesting in terms of physics is because they give us access to regions of extreme physics that we can't possibly test on the Earth. So very, very high ejection speeds, very high Lorentz factors, far in excess of anything that you would see in CERN or in AGN for that matter, regions of strong gravity, and we think large magnetic fields. And of course, we are also able to use them increasingly for probes of the laws of physics. If you don't care about the physics of gamma ray bursts, you might also be using them as beacons in the distant universe. My redshift estimate may be out there. There may be higher redshifts yet discovered. I think that's the highest I've heard of so far. And they are very, very bright. And so you can use them to probe the intervening material, either in the host galaxies where they occur, or all the way along through the cosmic distance path. And so they're interesting to cosmologists, and they're interesting beyond the field of gamma ray burst physics themselves. But of course, we cannot predict where they'll occur on the sky. They can happen at any time of day or night, at any position in the sky. And that is what has made them technically very challenging. They were first discovered in the 1970s with Earth-based satellites looking down at the Earth violations of the Nuclear Test Ban Treaty. And the detectors showed these flashes that was quickly realized that these were extraterrestrial. But the localizations were so poor that the rest of the field of astronomy couldn't follow them up. And it was actually the first optical and X-ray afterglow that was discovered in the 1990s that really opened up this field. We know they're isotropically distributed on the sky, and until those afterglows were found, the big debate was whether they were actually truly cosmological objects or whether they were objects distributed in the halo of the Milky Way. We now know they are cosmological. And so they're observationally and theoretically challenging. And this plot here just kind of gives a quick summary, really. So whatever your favorite type of object, transient object or high energy object is on here, you can see the vast timescales that gamma ray bursts cover and the vast energy scales that they cover. And in fact, this plot doesn't show all of it. In fact, some of the gamma ray prompt timescales can be less than a second. When we start to look at longer wavelengths, they can continue to emit in the radio for days, weeks, months, and years. And so we also have a big observational space that we're trying to probe. As I said, there are two main types of progenitors. This is the sort of the classical model that we think of. However you form your black hole with your accretion disks, we have two kinds of progenitors. And really these sorts of models came originally from an observational perspective, where when we look at the high energy gamma ray duration, we see it split bimodally around about 2 seconds, so short bursts that had hard spectra, so they produce more high energy gamma ray photons, were seen to have durations less than 2 seconds, sometimes down to very sub-second timescales. And long gamma ray bursts were defined to be greater than 2 seconds. And of course, there's an overlap region in the middle, and we see some hybrid objects. But that was originally discovered by Crisocoglietto in 1993, and that really has been the paradigm in our field. These have been the two working models for those two types of populations. And it was actually the first discovery of gravitational waves with an optical counterpart and a gamma ray burst in 2017 that really confirmed our short burst scenario. And previously to that, the first discovery of a supernova remnant or a signature of a supernova in the light curve of a long gamma ray burst that convinced us that we were along the right path here. Of course, we are able to diagnose some of these properties by looking at the radiation, and whatever your progenitor is, we think that the blast wave model, the so-called blast wave model, the standard fireball model of GRBs, the radiation is produced when we have a relativistic jet. Shells catch up with one another, they produce prompt gamma ray emission, and then that internal shock continues to drive an external shock out into the circumburst medium that then produces the longer-lived afterglows that produce wavelength radiation across the entire electromagnetic spectrum from high-energy gamma rays right through to long wavelength radio waves. And of course, the idea of these producing relativistic jets is not ludicrous, because we see jets in all sorts of cosmological and galactic sources, whether that's in our own Milky Way like SS433, whether it's nearby Cepheid galaxies like NGC 4151, or it's supermassive black hole driven systems like AGN, such as M87 and Pictoray. I know we've had some talks on those earlier on in the week. Now, the thing to remember about gamma ray bursts is they will always be unresolved point sources to all current and future instrumentation. So I don't expect us ever to have beautiful spatially resolved images of their jets. So we actually have to infer all of their physical properties from the light curve behavior. And it was really groundbreaking when it was first realized back in the early 2000s that, in fact, the temporal decay of the optical afterglow really proves that we have physically collimated jets. It's not just a relativistic beaming of the radiation, but it's actually physically collimated emission. And the way polarization comes in here is there are some very clear theoretical predictions that show that if you do have a jet and you're observing it slightly off axis, you should actually see a characteristic flip in the polarization angle. And Klaus Versimer and team, we discovered that in 2014, that we actually had finally proven this rotation in the polarization angle. So we have a very nice image in our head as to how these things are working when we're looking at our light curves and having to infer the geometry and the physical properties of them. But as I say, my main focus really has been understanding the magnetization. And this is probably quite unique in astrophysics, where we had some very clear theoretical predictions. There were two competing models when I started to build up my group to do the observations. There was the standard internal shock model, which I showed you the picture of. It's a synchrotron model. And the idea is that you have a baryon-dominated jet that creates a tangled magnetic field in a thin shock layer as the shock wave propagates out into the circumburst medium. You have high variability in the gamma rays, that's the internal shocks. But the problem with this model is that it's a very inefficient way to turn bulk kinetic energy into radiated energy. And there are still some issues unresolved about the details of this model. The alternative is a pointing flow. So you have large-scale ordered magnetic fields that are revected outwards from the central engine. This model is very successful at accelerating and collimating the relativistic plasma, but dissipation is a challenge. So these jets can go on for a very long way without actually radiating. And we know they radiate because we detect them. And so really, when we started to think about how we might take these studies further, the origin of magnetic fields in the universe generally is still unknown, but were very important to understand the energy dissipation and deposition for these explosive energetics. And the dissipation through magnetic reconnection, that's also a third model. The energy transfer details are still being worked out, but I think we have a much better idea about the magnetic fields in GRBs now. The way my team decided to approach this was by looking at the afterglow. And what we were developing when I was in Liverpool and at the University of Bath, we were building the world's largest robotic telescopes, the Liverpool telescope and the Faults telescopes. These are 2-meter optical robotic telescopes. They're fully autonomous, so not Q-scheduled, and there's no human intervention. And I joined Liverpool just as they were building this telescope, and there was no gamma ray burst group, and I was working on galaxies and AGN, but it seemed a great opportunity to use this telescope, which is not dedicated for GRB, so we had to develop the technology and the software. And theoretically, we have 3 different types of light curves. And I've shown a schematic here. We have a forward shock that propagates out into the interstellar medium. Its brightness rises more gradually and fades away more gradually, and it's a standard forward shock synchrotron. The reverse shock propagates back into the oncoming flow and is the last stage at early time where you are able to probe the fundamental properties of the fireball. And theories predicted that the reverse shock should be polarized and the forward shock should be unpolarized. Now, if you get your telescopes on to these bursts at late time, so a day after the burst, then the power law decays all the forward shock, and you cannot distinguish between these scenarios, and you certainly can't probe the reverse shock. So what we realized was that our optical robotic telescopes were ideal because we were getting on just in the first few minutes of the bursts because of the NASA SWIFT satellite, which actually sends down real-time gamma ray burst discoveries and their localizations, which were accurate enough in position for us to go immediately on the high energy gamma ray positions. We did not have to wait for an X-ray afterglow to be identified. And so what we then wanted to do was really test this idea out. And as I say, there are 3 different ways of combining your reverse shock and your forward shock. And the way they're combined in the physical properties of a GRB depend on the microphysical parameters and the magnetic fields. And so this gives you an indirect way of probing the magnetic fields. So you can either model these light curves. If you just have a type 3 at the bottom, a forward shock, and that tells you something about the magnetic fields. You may have a mixed model where you have part of a reverse shock combined with a forward shock, and you may observe at any point of this, or you may separate them very cleanly and observe across the whole light curve. We actually looked through the literature a few years ago, and we compiled a pretty large sample of about 118 GRBs, and we found only light curves that only showed 10 reverse shocks that actually had spectroscopic redshifts. We did all sorts of parameter comparisons and energetics, and the one key thing that stood out for these bursts was that they had fainter than average forward shock emission at later time after 10 kiloseconds compared to the whole of the SWIFT sample of thousands of bursts. And what this really hinted at was that those bursts that were showing reverse shock emission actually had high magnetization. And for those of you who are familiar with these parameters, you can see the numbers. So this hinted that we had magnetized baryonic jets, not pure pointing and not pure hydrodynamic. And you can see here some of the fits to the light curves, and I encourage you to look at Yuri's paper there. We were surprised that we didn't find more bright optical flashes. That was what the whole field expected to see when we started to have these direct localizations and robotic telescopes following up quickly. And what we did was we modeled, and we realized that actually maybe the reverse shock, because of the energetics, might be flashing in the infrared and radio bands. So any of you who have infrared telescopes, and particularly if you have polarimeters, I suggest that you still keep looking at these things because we still haven't found many of these reverse shocks. We did some modeling in the radio, and we actually were able to predict with some simple models accounting for synchrotron self-absorption at early time, and then modeling the different components of various different physical properties, some very simple models to show how the reverse shock should evolve at later time if it's to be detected in the radio. And then we did some quite sophisticated Monte Carlo simulations, putting in more physical properties for the interstellar medium and other properties for the magnetization of the burst. And really, to summarize that, the sweet spot is that radio reverse shocks should be detectable between about 0.1 and 1 day. And the detection of these should be easier for bursts with later optical peaks, higher isotropic energies, lower circumburst medium densities. And if you observe at frequencies above a few gigahertz, you avoid the synchrotron self-absorption and you should be able to see the reverse shocks. My team internationally, my collaborators around the world have started to do this. We made the first detection of a reverse shock with ALMA a few years ago. That was published by Tamoy Lasker. And we subsequently made the first detection of a polarized millimeter afterglow. But these still are incredibly challenging observations to make when you are triggering them at the telescope. And it's the hope really that the SKA will be the breakthrough instrument where we'll be sampling these across the sky at different times in large numbers. So as I said, the other way that I like to probe magnetic fields is directly through polarization. And I'm sure I'm preaching to the choir here. I put a few examples in early on as to why polarization is incredibly challenging and actually quite controversial. So these were groundbreaking observations at the beginning of the field. And you may or may not have remembered the big result that came out from the RESI satellite. It was published in Nature and it was thought to be 70 to 80% polarized. Obviously, coherent synchrotron radiation can only get to 70%. So it was a hugely surprising result. Another team actually analyzed the same data and came to the conclusion that the polarization was 0. So you can imagine the consternation at the journals. But what this shows is actually it's incredibly hard to do gamma ray polarization reliably because you are actually working with systematics and statistics. You don't have any other source in the sky simultaneously to calibrate against. And you can see some other facilities that then came along and also made claims of polarization. And I think these are very exciting. They've remained somewhat controversial in the community. And we now have new satellites like Polar and Astrosat that, of course, are doing great work here. But it still remains a very challenging thing to do. And at the bottom here, we have this very nice integral result, which was quite a high redshift burst, nearly redshift 3. And Diego Gotts and his collaborators here did some really nice work and putting some constraints on quantum gravity models. So my team specialized particularly in optical polarization, where there was no instrument worldwide that could do this. But actually, once we started to develop our instrumentation, it's actually a little bit more straightforward to calibrate than in the gamma rays, but it complements all of those other wavelengths. At late time, certainly discovered with large telescopes back in the 1990s, optical afterglows were seen to be just very, very low polarization, so a few percent probably induced by dust in the interstellar medium. And this was important in confirming jet models and actually jet geometry. So they were groundbreaking observations at the time. But what we realized was that if we really wanted to understand the fireball and the central engines, we really had to get on at early time. And we had unique telescope technology and access to those telescopes to be able to do that. And what we really wanted to do was provide this key discriminant between the hydrodynamic and the magnetic models. The theory, as I said, predicted that reverse shocks should be polarized. We understood the light curve shape, so we know how to find a light curve that will tell us whether we have a reverse shock or not. So it seemed pretty straightforward to go ahead and just measure the polarization of that light. I should say at this point, without sounding too sad, we had no money and we had no instrument, so we had to be pretty innovative. And what we did was we spoke to Dave Clark at the University of Glasgow, and he'd published a novel design for a small stellar polarimeter that he'd never built and put on a telescope in anger. And so we decided to copy this design in the first instance. We called it Ringo, not because it was Liverpool or the Beatles, but because it actually produces rings on the CCD. The reason it produces rings is because we put a deviating prism and we glued it to a piece of Polaroid and we spun it at 550 revs per minute, 24/7, and we put that instrument on the telescope. So what you can see here in the top right-hand corner is the sort of trace that you get for a polarized source. You correct for the instrumental depolarization, then you get this very nice 2 theta sinusoid, which will be familiar to any of you who work with polarization. We were able then to fit to that sinusoid and extract the polarization properties. We put this in our telescope, and in Easter 2006, the universe obliged and gave us this GRB. You can see in the right-hand panel that the light curve looks very classical forward shock. It goes up. We have a peak, which is the time of deceleration of the fireball, and that was exactly when we made the Ringo measurement. This was the earliest ever polarization measurement of a GRB, made just 203 seconds after the GRB. And we had a very robust upper limit of 8%. And so we confirmed here that well, our model was that we had equal contributions from forward and reverse shocks, but I think now probably this is an unpolarized forward shock. We waited 3 years for another burst that was bright enough. This was GRB 090102. And you can see here that we have a steep, shallow gradient on the optical light curve. And this is actually us catching the tail end of a proper reverse shock. And we were very excited that this was 10% polarized. This was a very robust result. And of course, when you look in the field, we've also got lots of other stars in the field against which we can measure and compare our gamma ray burst. We went back to this field many months after this for several repeats to make sure that our instrument was stable, both in terms of position and in time and in different observing conditions. And so this was a very robust result. We did publish it in Nature once we convinced the editor that our result was robust and that we could cross-calibrate with all these stars in the field. And that was, again, an earlier exposure. That was 160 seconds after the burst. And we really looked at how to model this, and we favored large-scale ordered magnetic fields in the expanding fireball. The light curve shape ruled out that it was just a geometrical effect, and the degree of polarization meant that it was unlikely that we just had scrambled patches in a thin layer. So wonderful, like all great scientists, we then had a unification scheme. We'd solved things. We had an unpolarized forward shock and a polarized reverse shock. And we were able to model this with different magnetizations. But we realized that 2 is not a very large sample. And also we were missing an awful lot of information. So this just shows a fairly long gamma ray burst that lasted for about 1200 seconds. You can see in the black how variable the gamma rays are. And you can see in the optical how variable the optical is too. Now with Ringo, we were making a single integrated measurement, and we were not getting any of the time variable polarization information from that. It was also quite hard to deal with the rings, and we realized that if the rings ever overlapped on the sky, we wouldn't be able to find the 2 theta sinusoid, and we were also contaminated with a lot of sky photons, and so our sensitivity wasn't great. At this time, EMCCDs were becoming inexpensive, and we realized that we could re-engineer Ringo to produce a new generation, Ringo 2, with a fast readout EMCCD. We took away the deviating prism, and we slowed down the Polaroid to 8 rotations per second and read out the camera every 125 milliseconds. We had nice images, and we could then stack to whatever sensitivity we needed because there was no readout noise on the EMCCD. And this was a very exciting change. This was the first burst that we detected with significant polarization. We did this at 240 seconds after the burst. You can see the image on the left-hand side is much nicer now. It's like a proper photometric image. We just do point source photometry. The GRB was very bright, and in fact, it was very highly polarized. Stacking it all together in time and just comparing it with the stars in the field, you can see all the stars down here. This is just the effect of the stars, the fainter stars, so you have to have higher polarization to be convinced, but the GRB stood high above here. So we were actually sure that this was already a robust result before we then separated the stack in time. And as I say, we have time resolved polarization. So when we started to break our data up into time bins, in the top you can see the evolution of the polarization. It was high at 30%. This is still the highest ever optical polarization detected. And it decreased down to about 16%. Underneath, you can see the light curve. We clearly detected a very dominant reverse shock at early time, and you can see the forward shock coming in and dominating at late time. And so our interpretation of this polarization, particularly because the polarization angle was only varied by about 15 degrees over the time window, is that actually we're dominated by the reverse shock. We're diluted by a little bit of the forward shock. And actually, if the forward shock is unpolarized, then the intrinsic polarization of the reverse shock is as high or greater than 40 degrees, and that's getting to the maximum it can be. The problem with Ringo 2 was that we were doing this over a broad color, so we had no color information, and that made it quite hard in general to be able to distinguish reverse and forward shocks, which have different color behaviors. So we invented Ringo 3. It was a much more complicated instrument, and we've now modeled all the spectral energy distribution. You can see that in the comparison with SDSS filters. So it's a bit bespoke, but we now understand the throughput very well. We kept the general engineering, and we actually put 3 dichroics in, so we could now do simultaneously 3 colors and polarizations across all those bands. This was a really nice burst that we got when we were still commissioning the instrument. It was very variable. It had X-ray and gamma ray flares, and you can see here in the colors the exquisite time sampling of the Ringo 3 light curve in 3 colors, and we were actually able to follow all of its evolution simultaneously with the gamma ray and the X-ray light curves. We had an upper limit of 12% because, as I say, we were still in commissioning mode. Otherwise, we would have probably made the first detection of polarization of prompt gamma ray and X-ray emission. Now, I mentioned that we think that forward shocks are unpolarized, and this was our next discovery shortly after that previous burst. And we published this last year, actually, because we did a lot of work on this burst, and we think this is the earliest ever detection of a forward shock and the measurement of its polarization, which came out at 2.8% at just 168 seconds. We modeled this in great detail. Nure Giordano Mitjens led the paper, and it's just a beautiful forward shock. It just fades all the way down. We think that the reverse shock happened much much earlier, and this is actually a very high energy burst. So now if we combine that with the previous result, we know, or we accept, that forward shocks are unpolarized. Then, as I say, the reverse shock in the 2012 burst was very highly polarized. Now, we've started to detect gamma ray bursts in the TeV, which is a very exciting precursor to the building of the CTA, the Cerenkov telescope array. We hoped that the CTA would be able to detect GRBs, but we had no guarantee of that. And in recent years, there have been 2 or 3 very high energy TeV sources that have been detected. Again, showing here the exquisite time sampling of Ringo 3, which you can see here in the three multicolor light curves here. These are the high energy light curves. And we modeled this as actually a reverse and a forward shock. This was a very famous burst. Many teams got onto this burst. But what we did that was unique was actually to measure this polarization. And with the Liverpool telescope, we were on just under 100 seconds, and we saw low polarization. We were down at just at 2 to 3%, which surprised us given how bright this burst was. But what we were able to do was actually combine some data from the Master telescope, which is a Russian network of robotic telescopes, 0.6 meter telescopes around the world. And they are able in some way to probe the polarization. Where they have two parallel tubes. And again, I can explain that in questions if people are interested. So we worked with them and helped them to calibrate their data. And we measured about 8% just at 50 seconds after the burst. And so you can then see that connection. They didn't have the sensitivity to go beyond that, but we did with our 2 meter telescope. And the way we modeled this was actually by suggesting that the magnetic fields actually collapse and dissipate and give their energy up during the prompt phase. And that's why we don't see long-lived high degrees of polarization. And that's actually what generated the energy reservoir to power the TeV emission. And again, doing this in the CTA era, we'll be able to do this with large numbers. This was also the first detection of polarization in the millimeter, and we made that detection with the ALMA array, and Tan Moy published that in his paper in 2020. Now, we have made prompt optical polarization measurements. This was the first, and I think still the only. Nora Troja led this paper back in 2017, and we published this in Nature. This was a really lucky break. We had a very weak precursor that triggered SWIFT and alerted telescopes around the world to the fact that this burst had happened. And then shortly after that, there was then a very, very bright prompt flare. So if we hadn't had that precursor, we might not have been on source. So we had a beautiful view of this. We were able to model the reverse and the forward shock and the prompt emission and separate all of those components spectrally, excuse me, as well as energetically. And we measured here for the first time polarization of 8% in the prompt optical. So again, this holds great promise and is a field that I hope will develop and open up in the future. So putting all of this together, I know this has been sort of a fast whirlwind tour, but I think now we're starting to get a very nice coherent picture as to how to probe the magnetic fields from the very earliest prompt phases through the reverse shock and out into the later time forward shock, whether you're interested in the geometry of the bursts, whether you're interested in the jet physics and the magnetic fields, and ultimately whether you're interested in the progenitors. And we are favoring magnetically driven baryonic jets with large-scale ordered magnetic fields advected from the central engines. And we've also tried to make some polarization measurements of the first kilonova source, which was detected back in 2017 with a gravitational wave counterpart in a GRB. We did measure polarization at a day and a half using 8 meter class telescope, where we think that the flow is blue and it's lanthanide free. And then the polarization decreased as the burst evolved and became red, as the kilonova became red. And we started to see the lanthanide rich flow. So we've actually got a really nice discriminator for these sorts of sources as well, not just the relativistic jets. And we can start to look at the geometry, and we hope that we'll have more of these bursts in the future. And we published that again in Nature, led by Stefano Covino. And you can see here in Buller 2019, some modeling to predict for future observations. And so I think we now have this very nice polarized view in time, right from the very earliest prompt gamma ray emission all the way through prompt optical, through early forward and reverse shock, polarized and unpolarized, all the way through out into the kilonova and merger remnants. So we're starting to get this really nice complete picture. And of course, you will hear talks from colleagues who are using new X-ray missions like IXPE, and they're starting to find some exciting results as well. So hopefully we'll be able to put all of our facilities together and really do this at scale with many more bursts than the few that we've done so far. And I wanted to finish really with this new progenitor paradigm. So there are a number of really interesting talks that are in this conference, and also backing up papers that came out just before Christmas. And here is the classical short hard burst plot in some form. So you have these supposedly compact binary merger short bursts, and you have these core collapse massive star progenitors for the long bursts. And this paper came out in 2021, suggesting that this GRB here was actually the shortest collapsar model. So a short GRB with a supernova. They actually found a supernova component that they claimed at late time. And they suggested that this is just at the edge of the short burst cloud, and that it may be a merger origin with a supernova. So it then starts to become a collapsar class. And so that was quite an intriguing paper. And then in 2022, a very bright burst happened, and there were a number of papers that were published in the same edition of Nature. And apologies if I've missed anybody else's papers out here. And it sits classically in the long GRB cloud here. But authors suggested that they had found a kilonova component, which of course is characteristic of a short merger origin over here. And so we're starting to see, some really interesting dichotomies starting to come up here. And do we have a much broader parameter space, of which we've only sampled these two apparent bimodal populations? And then tying it together, there was a short burst that we published just before Christmas in November, and Nuri Giordano Mitjens will talk about this in the later session. And we suggested that this is a classical short burst. It has extended emission in the high energies, and we've suggested that the progenitor is actually a supermassive neutron star, so it is a merger remnant, but that merger remnant doesn't collapse immediately to form a black hole. And Nuri will explain why we think that, but in fact we produce a highly magnetized spinning magnetar, and that's the first ever discovery, I think, of very early time optical thermal emission. And I think that the future of wide field surveys with things like the Nancy Roman Grace telescope will actually help us to find these things without being triggered from the high energy satellites. We'll actually be able to find these thermal components and test these progenitor models and really open up this diagram and understand the true parent population of our gamma ray bursts. And so to finish, I think we are entering a revolution in multi-messenger time domain science. We've prototyped these things. We've actually advanced the physics greatly over the last decade and a half. We understand a lot, but we're now going into a very different regime. So we have neutrino experiments that are starting to really give us exciting results for cosmological neutrinos. And there are a number of neutrino experiments that will be coming online soon. We obviously have routine detection of gravitational waves now. We have a suite of space facilities that are up there and new ones that are to fly soon. The Cerenkov telescope array is approved and being built, as is the SKA. So in the radio, we now have the construction of the SKA happening there in South Africa and Australia. And the Large Synoptic Survey Telescope, now called the Rubin Observatory, is already in advanced stages of being built and will actually be streaming millions of transients to us a night, not just 100 or 200 GRBs a year. And of course, we continue to develop our advanced technologies and our advanced automatic and autonomous robotic telescopes around the world. And so I think the future is bright. I think we have lots to understand. And my plea really is to the theory colleagues at the conference. As observers, we will be drowning in data and we will be mining them and trying to interpret them. But what we would really love from you are very clear testable predictions so that we can interrogate our data in a different way. Thank you very much for your time, and I'm very happy to take questions if there's a few minutes left.